HPing 3. If we want to discover network devices, whether they're local or remote, and they're not responding directly to ICMP ping requests, we can still verify that they exist using TCP and UDP options. HPing 3 has those options and a boatload more. Let's begin. I'd like you to imagine that you and I are sitting at a couple of computers, and from a command prompt we type in ping www.cbtnuggets.com and we press enter. And what do we know based on this? Well, taking a look at the response, we know that DNS is working because we used the name CBT Nuggets and it gave us back an IP address. Well, that's great. However, we're not getting a response. Does that mean that that website is not up? And the answer is very likely no. It just means that ICMP is being filtered. What other tools can we use to validate that there really is a device sitting there? Well, we already have a couple in our tool set. We have the Nmap and Zenmap that will both do it. And I want to share with you another command line option that can do the same thing, and it is called HPing. HPing 3, the current flavor, replaced the predecessor HPing 2, and before that HPing. It does pings, but it can do it not just based on ICMP. You can actually do it based on SYN request and other flags in the TCP header. You can do ping requests with UDP, looking for an unreachable message coming back from that device to trick the destination device into responding back to indicate that it is sitting there. In addition to doing that host discovery to find out that devices are there and maybe what ports are open, it can also do fingerprinting, very much like some of the other tools that we've discussed. With fingerprinting, if we know the initial sequence numbers are predictable, we can map that over to a specific operating system or family of operating systems that behave in that way. It can also act as a sniffer, we can use it as a flooding attack tool, and we can even do covert channels and initiate file transfers using HPing. So we try to ping from a Windows box. We could also ping right here from a Kali or a Backtrack distribution. Ping www.cbtnuggets.com. There's no response, and that is very likely because there's ICMP or ping requests specifically being filtered. So we're going to do a Control-C to stop the attempt of that. And now let's use HPing to go ahead and verify. So when I talk about HPing, I'm talking about HPing 3, the current flavor of it that's in Backtrack and Kali. Now, how do we get help? Do you remember? How do we get help for commands if we need it? Now, if you're saying, Keith, I know we could use the man pages, and that's absolutely true. So type in man space, the name of the command we need help with or want information on, which is HPing 3, press enter, and there's the man pages. So we can scroll up and scroll down through them. That's all the documentation. So we'll hit Q to quit that. How else could we get help with this command called HPing 3? And you got it. Just type in HPing 3. And with a -H, and that will give us the help. Now, there are dozens and dozens of options and switches based on if we're going to do TCP-based or ICMP-based or UDP-based, etc. So what we'll do is let's do a few examples together, and as we start using some of these switches and options, I'll describe what they are. And as we use this tool together, I'll introduce the switches and options that we're using. I also have, just for you, in the Nugget download area under Nugget Lab downloads, I've got all the commands I'm using in this Nugget, so you can go ahead and use them as a reference as well. So let's use HPing, and the syntax we're going to use is HPing3-S, and the -S is right here on the screen. In fact, let me get my pen out. So we're going to be using TCP. It's going to use a SYN request going to that server, and the port we're going to actually be sending it to is port 80. Now, even if it wasn't port 80, let's say it was another port, it's very likely we could get a response back saying, you know what, I'm sending a reset, I'm not listening on this port, and that would also indicate that the device is there. So the -S is for the TCP SYN request. That's the name of the site we're going to go see. That's the port number. And the -C2 represents, I only want to do this 2 times. So a count of 2. Otherwise, it would just go over and over and over again until we do a Control-C to stop the process. So let's press enter, and sure enough, we have a response from port 80. So we've just verified our connectivity over to www.cbtnuggets.com, at least on port 80. Now, that means routing is working for the packets going back and forth. And if that was our goal, that's fantastic. We also happen to get, as a bonus, some timer information, which is another valuable tool in assessing if there's delay, for example. Maybe we have a voice over IP application or something else, and that could be used as an indicator of the delay to a specific site. Here's another example of how we can play with some of the ports involved. We'll do HPing-S, again for a TCP SYN request. We'll specify I'm going to use a local IP address on my private network for this one, 192.168.1.38, which is a device that does exist on my local network. And take a look at this option right here. We have this -P for port, and the ++50 says go ahead and start at port 50 as a destination port. And then the -C5 says go ahead and repeat it 5 times. So it should send out a request going to destination port 50, then 51, 52, 53, 54 for a total of 5 packets being sent. Now the interesting thing is that if we send a packet out to a server or a device and the destination port is port 50, if that device replies back to us, the source port is going to be 50, and it's going to come back to whatever our source port was that we initialized it on. So, for example, if we use port 6783 as our source port going to 50, the response coming back is going to be from 50 going to 6783. So for the reply packet, it would say, oh, the source port is 50, and the destination port is 6783. Just another way if we wanted to play with the ports involved in trying to identify devices that are responding or available, that's another way we can do it. So let's test this one as well. So we have 1, 2, 3, 4, 5. Fantastic. And it's interesting, though, for me at least. It says source port is 50, and that's because we're looking here at the reply packets that came back from that device. So 50, 51, 52, 53, 54. There's the time it took for that to come back, and the flags involved. So the R is a reset. That device that we sent this to at .38 didn't have services listening and waiting on ports 50 through 54. So it got the TCP send request, and it sent back a reset on each one of them, for each one of them, saying, you know what, I don't have any services open on that port, go away. And again, we get some timing information as an indicator of the latency for packets going to and back from that site. If we just want to do a standard type of a ping, we could of course use ping itself, or with hping we could actually say I want to ping the entire subnet. We could also specify that we want to go ahead and do it not in order, not start with 1 and then 2, and it can randomize that for us. So this syntax right here, the -1 says I want to use ICMP for this. So hping, by default, it wants to use TCP. So by specifying a -1, we're saying nope, just use traditional ICMP. The .x refers to a variable in that last position, so it'll go ahead and it will ping all the possible IP addresses in that subnet. And this option right here, the --ran-dest, that says don't do them in order. Go ahead and maybe pick 5 and then 38 and then 27 and 99 and 250 or whatever, but don't do it in order. The -I says what interface do I want to use, and you can specify the interface you want to use for this actual ping. So we'll go ahead and launch that by pressing enter, and it's going to go through and it's going to ping virtually everybody. Now, you can wait for this all to complete, or if it gets the information that you need, you can do a Control-C to go ahead and stop. So I'm going to go ahead and do a Control-C and not wait for the entire range to be done, but you can get an idea, for example, as far as the response time it took to get information back from various devices, and it was not doing them in order. Started with 29, then went to 2, then went to 38, and eventually it would have gotten to every single device. And I guess we should say every single device that responds to ICMP-based request would go ahead and send a reply back. Those that weren't using ICMP or had blocked it or not responding to it. But that, my friend, is why we have the TCP option that we looked at previously, so we can find out about those guys as well. Another option that we can use is to go ahead and make a request of a timestamp from a device. Instead of just an echo request, we can use an ICMP request for a timestamp. And if your device that you're aiming this at responds to that, that's another way of validating that that device is present. So the syntax for that one is right here. The -1 once again represents we're doing ICMP, and this option right here says we're requesting the timestamp, and the -C2 says I only want to send 2. Otherwise, if we leave off that counter, it'll just keep sending them and sending them and sending them. So right here we have 0% packet loss, which is fantastic. We know that device at this address, 192.168.1.1, is there. The reason I point this out is that if this device right there had been configured or didn't allow responses to ICMP echo request, it might allow the response for the timestamp, and that's yet another way we can validate and verify that a device is sitting there. As we give hping a little workout here, another option is to go ahead and ask for the mask. Now, normally, a computer today won't reply to that. Somebody sends an ICMP message with a mask request, and the response back is going to be, nope, I'm not going to tell you what my mask is. You don't need to know that. You just send me packets, and I'll process them. So for this packet right here, that's exactly what this is. I'm doing HPing 3-1s for what? ICMP, perfect. This is the destination, and this is the actual information I'm sending. I'm asking for the ICMP address request. The mask request effectively is what that is. And the C2 is the count. How many times am I going to send this? Now, I had 100% packet lost. I got no information back from this, and that's very likely because this device, which happens to be like a Palo Alto firewall, it doesn't respond. It's not willing to give up that information. Another option with HPing is the option to do a scan. Now, by default, it's going to be doing TCP unless we specify that we want ICMP or UDP or something other than TCP. So this -8 right here represents a scan. There's our range. We want to scan ports 50 through 56. And we're going to specify this is our destination. Now, that's a DNS server from Google. And what this is going to tell us is whether or not any of those ports are open on that server. Now, DNS requests are typically UDP, and it's port 53. However, very many DNS servers also have TCP, port 53 also open. So if this is true with this DNS server of Google right now, this should give us a response back with the port that it found open. So we'll press enter, and it launches it and says, you know what, sure enough, it scanned 8888, ports 50 through 56, and it said I found 53 was open. There's the flags involved in the packet that came back, and all the other ports, 51, 50, 52, 54, 55, 56, they all were not responding. There was no open services on TCP on those ports. Now the question is, does DNS really need port 53 for TCP open? And the answer to that is depends on what you're doing with that port and with that service. But what we do know is on this server right now, or at least one of the servers that's responding is 8.8.8.8, and there could be any cast addresses, so they could have hundreds of devices sitting at 8.8.8.8. In any case, we know that this server that we just talked to, it is open on port 53 at this moment. So let's say we have a device, it's not responding to our TCP SYN request, it's not responding to ICMP anything. How can we still test it? And the answer is we could try UDP. Now, UDP is, connectionless. It doesn't do acknowledgments or sequence numbers. However, we can make requests to a specific UDP port. So the fun thing is that if we send a UDP request and that device burps, it does anything, it responds back to us, he's just given himself up. We know that there is an entity there at that IP address because he just gave us some feedback, or something that pretended to be that device gave us some feedback. So to launch that, we would use this HPing, and we're going to use -2. Now -1 is for ICMP. -2 represents that we want to use UDP. There's our target. Again, I'm targeting internally to my private network. I'm specifying the port I want to send it to, and that's the count. So with that being said, let's go ahead and launch it. And look at this. Oh, that's great news. Look at this. We got a response. And that response was right here. Check that out. So ICMP port unreachable from 192.168.1.6. So now we've looked in this tool alone at 3 different methods for validating a device exists. We could use TCP options, we could use UDP, or we could use ICMP. If we get responses on any one of those methods, that device is validating that it exists. Another tool that we played with, Scapy, had the ability to craft virtually any packet we wanted to, and we have a lot of flexibility with HPing as well. For example, let's say we wanted to send a ping message. By default, this with HPing is going to be TCP based unless we specify ICMP or we specify UDP. In this case, the -F says we're going to go ahead and modify the flag, the FIN flag, from a TCP header. The P is the push, and the U is urgent. So we're effectively, they call us a Christmas tree ping because we're lighting up the flags, the F, P, and U, and we're sending this packet to this destination. And we're going to do it only 3 times. Now, if you leave off the count, again, it will just continue doing it over and over again. So how could we actually use something like this? Well, let's say that we are reading a periodical and it announces, hey, if you send this, this, and this to a blah, blah, blah version X machine, it's going to respond with the SAM database, or it's going to respond with information that it shouldn't, or it's going to totally wipe out the protocol stack. It's going to be a good DOS. You could go ahead and leverage that. Now, you could use Scapy to do it, or you could use this tool HPing to do it based on what we're trying to craft. But we're simply adding tools to the tool belt of being able to effectively craft packets and send them out right here from Backtrack or Kali. So let's launch this and see if we get a response. Now, the 1.38, I believe, is a Cisco router on my local network. I know I have a Cisco router on my local network, and we could verify that. In fact, let's just do that real quick. Let's go to R1 and do an show IP interface brief. And sure enough, that is indeed his IP address right there. So if we go back to our Raspberry Kali box, we sent 3 packets and we got responses, 3 of them. So again, that's just another mechanism for validating a device there. And if specifying certain flags in a certain order was important based on the vulnerability we're trying to exploit or some other discovery process, again, we can craft them right here with HPing. The initial sequence numbers for a device, if they are predictable, that is a vulnerability. And there's some older operating systems that do have very predictable ISNs. If we wanted to verify the ISN sequencing that a device was using, we could use HPing to do that. So HPing 3 using TCP, here's our target, which is 192.168.1.38. And I'm going to go ahead and pause this. So here's the play-by-play. The -Q simply says we want to see the sequence numbers. So we can take a look at the output and we can see if there's a predictable sequence number that's going to use after a period of time. And again, older Windows operating systems like Windows NT and Windows 98 had predictable and sometimes the same initial sequence number that they would begin using. So by looking at the initial sequence numbers they're using, we could identify by comparing those initial sequence numbers to a flaw or an older operating system that used it. And that's also going to give us insight into what operating system is running on this system. As an example, let's compare that host, which was .38, which is a Cisco router. Let's compare that against another system at .21, which I believe is like a Windows XP box. And we'll take a look at the difference in the output. So the initial sequence numbers, you'll notice, are a lot shorter. And if after a period of time they became predictable, that would definitely be some type of a vulnerability that we might be able to leverage with an exploit. I'm going to hit Control-C to stop the sequencing. Another example of how we could use HPing is, let's say, for example, we knew that SSH was open on a network device. Now, how do we determine that? Well, we could scan for it using one of the many tools we've taken a look at in this series, including HPing. And then once we know it's open, or that it's an open port for SSH, we could go ahead and flood it. Now, what does a device do, a network device, if it sees a TCP SYN request? It's going to reply. And then what happens if it sees another one? It's going to reply. So a SYN comes in, SYN-ACK goes back, and we could do effectively, or try to do, a denial of service attack simply by flooding hundreds or hundreds of thousands of requests coming in. So again, presuming that port 22 is open on this system as a open port listening for SSH sessions, -S represents we have a SYN flag going to be set on the packet being sent. There's our victim, the .1.38, which happens to be, in this case, a Cisco iOS router running SSH. The -A is the address that we're going to source it from. Now, that's not really the address of this Backtrack/Kali system that I'm currently on. However, this would be a spoof source address. So we're going to send in TCP SYN request, and the SYN-ACKs are going to go back to, this could be a second victim here at this IP address. We're going to go to port 22, and the flood option says, "Dear Mr. Computer, just send those out, those SYN requests, as fast as you possibly can." So let's do this as a little fun. I'm going to launch this, and then I'm going to do Control-C. Just going to run that for 1 moment. So now that the attack is no longer running, let's go over to R1, and I'm going to use the up arrow keys to save me some typing here. Let's do a show control plane host open ports and press enter. And take a look at all these ports that are sitting there waiting, trying to establish all these SSH sessions. So here's the spoof source address, and there's the spoof source port numbers that we used, and he shows them as established sessions. He sent a SYN-ACK back to that address. It's really not fully established, is it? Because there's only a SYN, a SYN-ACK. There's no final acknowledgement coming back from the client sitting at 254. but now we've tied up a whole bunch of resources on this device. So let's go back and launch the attack again over on the Raspberry Pi. So let's hit the up arrow key there, launch it, and let it run. And let's going to let that run for a few seconds. Now, besides just causing a total consumption of all the available VTY lines on that system that we're connecting to, it's also chewing up a lot of resources. That's why with Network Foundation protection, we really want to make sure that we're limiting this type of an attack on our network core devices by doing something like rate limiting certain types of traffic so it can't overcome the CPU. Let's go back to R1 while this attack is still running. Show process CPU, and let's do sorted. So show process CPU sorted. This is bad news right here. Over 95% utilization, and that's our 5-second average. Over 1 minute, we're at 50%, and over 5 minutes, we're at 21%. But guess what? If I let this run, the attack just continue based on the current settings, all of these numbers eventually are going to be over 95%. Just based on the sheer amount of TCP SYN requests and processing that this router has to personally handle. It can't just forward a packet using the Ceph table. It has to think about it, respond to every single one of those requests. And again, this would be in the absence of the administrator putting in some safeguards to protect against this type of an attack. So I'm going to hit Q, and I'm going to hit the up arrow key again. Let's take a look at it now. And sure enough, it's climbing. And it'll continue to climb as long as I have that attack running. And effectively, this box is not going to be very efficient as an IP packet forwarder if all the CPU is consumed with handling those TCP SYN requests for SSH. Another fun tool that we can use is Traceroute. Now, Traceroute's fantastic. The way that Unix does it versus a Windows machine is slightly different. We have, with the PC, it uses the actual ICMP messages, and with UDP and iOS, it actually sends out UDP messages. If we want to do the equivalent of a traceroute inside of HPing, the syntax would be something like this. We're going to do -2, which specifies UDP. Remember, by default, if we don't specify a number, it's TCP-based. -1 is ICMP, -2 is UDP. And this says I want to go ahead and start at port 44444. The -T is saying I want to do traceroute, and the -N is saying don't bother doing name resolution. So if we want to get a list of all the hops between us and some destination like CBT Nuggets, we could run effectively a traceroute with this syntax. So it's showing us hop number 1, 2, 3, 4, 5. And I want to share with you something. Not every device in the path is willing to cooperate. So with traceroute, we're using a TTL function. So we set the TTL to 1, and we send out, and then we change the TTL to 2 and 3 and 4. Some devices, like some firewalls, don't mess with the TTL, so they're shown up as invisible. Other devices won't respond, and so this traceroute is simply trying over and over again. So at hop number 9, it responded, but hop number 10 isn't. This is important. If you want to skip hop number 10 and have it increase the TTL one more, simply do a Control-Z and it skips that. See, now it's on 11. Now, hop number 11 also doesn't want to respond to us, and that's okay too. A Control-Z again, that puts us at 12. 12 doesn't want to respond either. So they've got 3 devices in the path that are not responding. Very likely, at least one of those is a firewall that doesn't want to play that game. We'll do Control-Z again, and say hop 13, that's okay. No problem. And then it's now trying hop 14, etc., etc. I'm going to hit Control-C, and most of the other devices in this path are not responding. So here's another cool trick, though. Let's say you want to check out load balancing, and you want to see, I want to see exactly, maybe at hop 13, I want to see whether or not this IP address is still being used. For example, if we did this 10 times, and hop 13 was different almost every time, that means either at that hop or somewhere before that, we are doing load balancing. We're going over an alternate path to get to a given destination. Well, with this option, with HPing, we can say, you know what, I just want to see hop 13. So it'll manipulate the TTL so that only that device at that hop will see the TTL is exceeded and send us the replies back saying, hey, the TTL exceeded, I'm killing this packet, here's the response. Because that's how traceroute works by default. We're building this information based on the responses back, the ICMP messages coming back from those devices telling us that they kindly killed or dropped our packet. Now, just to round this out, let's say that the UDP traceroute function wasn't working. Could we use TCP for that? The answer is yes, we could. And to do that, we're going to use the -S, which represents a SYN flag is going to be set in the TCP packet, and we're going to specify, for example, port 53. So the intermediate devices don't really care about the TCP header information because they're not getting that far. All they see is the details regarding the actual TTL at IP, killing the packet when the TTL is exceeded and sending us the response message. So just like before, now that we're using TCP, hop number 10 doesn't want to cooperate, so we could do Control-Z, Control-Z, Control-Z. Hop 13 is cooperating. I'm going to do a Control-C as in cat to stop that. And take a look at this hop right here. It looks like the hop was 216, 182, 224, 63 for hop 13. And down here, hop 13 is 216, 182, 224, 249. So definitely a different device at hop number 13. And so now if we wanted to, we could focus just on that hop to take a look at all the different possibilities we might get back of the devices at hop number 13 who are saying our time to live is expired. So here's our syntax for HPing. The -S represents the SYN flag being set. www.cbtnuggets.com is the domain name. It'll be resolved to an IP address. P80 represents port 80. The -T representing trace route. The -TTL13 simply representing that we're going to set the TTL in this packet to 13. So we're not going to bother setting it to 1 and then setting it to 2 and then 3 and building this entire path. We'll set it to 13. So everybody will go ahead and forward it except for hop number 13, who's going to reach TTL 0, kill the packet, respond back to us. And if there happen to be lots of different devices at hop number 13 based on load balancing and the path that we're going through, it'll show up very, very nicely. This option right here says don't bother changing the TTL with your trace route, just keep it at 13. And the -N says don't bother trying to do name resolution as it was up here. So let's go ahead and launch that. And as it goes out, you'll notice that it's all hop number 13. And I have a whole bunch of different addresses. There are a boatload of paths. So I'm going to do a Control-C to stop that real quick. That way the syntax will still be up here if you want to see it. But check this out. Looks like we have 75 was used a couple times, and 51 was used a couple of times, and I don't see any other duplicates. So either at this hop or somewhere before this hop, we're taking alternate paths for most of our packets that are making their way to www.cbtnuggets.com. One other thing I'd like to share with you in this nugget is the ability to interact with HPing. Now to do that, you're going to type in hping3, the command, press enter, and that gives you a command line interface into the application. So from here, very similar to the function we had with Scapy, we can craft and carve out the actual syntax of the packet that we want to send. We can also use TCL scripts and get very, very fancy with the features we use within HPing. So in this case, if we were to send this packet, the source address would be 192.168.155. If we wanted to spoof and lie about the source address, we could definitely do it. The destination address would be this. The TTL would be that. We don't have to include those options. These are just, some of the IP header content that we're going to add. For TCP, so this is layer 3 right here. So for layer 4, we can specify the ports we want to have in use. So the source port, the destination port, any flags that we want to send, we press enter. It's going to go ahead and send this packet out on the network. And this is an example of how we could interact with HPing. In this nugget, we've introduced the concept of HPing, another packet manipulation tool that can be used to carve out and create the exact packets that we want to do untraditional like discovery of devices with pings using TCP, UDP, as well as ICMP. I hope this has been informative for you, and I'd like to thank you for viewing. Implementing a man-in-the-middle attack on an IPv6 network with Parasite 6. Let's begin. I'd like you to imagine that you and I have had a fantastic breakfast, our favorite food, and then we've shown up at our customer site and they have given us complete authorization to do whatever we want as far as providing some penetration testing and vulnerability assessment. And so we're excited. So I have a question for you. Let's say they have two different systems on their network. They have System A and System B. System A we could crack in about 5 minutes, and System B might take, 3 hours. So we have 5 minutes versus 3 hours. Which one are we going to do? And you might say, well, Keith, we're going to do it all. And we might. However, it's very likely we'd start on this one because we cracked this system, and that could lead us to more access and more access and more access. Well, here's the great news for us at this company. Unbeknownst to many people, IPv6 is running as a valid protocol stack on most computers that come to companies today. So unless they've taken specific steps to disable it, we can leverage IPv6 and how it operates to go ahead and compromise a network. And that's where it might take a very short amount of time to compromise a network, because maybe they haven't put in these security controls yet based on the IPv6 protocol stack, where IP version 4 is all locked down tight. IPv6 might be wide open. In this video, I'd like to focus on a specific tool called Parasite 6 that can let us do a man-in-the-middle attack against an IPv6 network. And this is so easy. It's a one-liner, and it works like a champ. So let's take a look at the basic process for neighbor discovery protocol. So let's say the Windows XP machine, it boots up, or the Windows 8, it boots up on the network. What does it do? Well, if it's running an IPv6 protocol stack, it's going to be looking for a router, and it hopefully gets a router advertisement, figure out what network it's on, and then run automatic configuration to get its host ID, the last 64 bits of its IPv6 address. It may have learned that it should be using DHCP stateful services through the router advertisement messages, or maybe just DHCP stateless services looking for a DNS server from DHCP. But at the end of the day, these devices are going to have an IPv6 address. Now, once we have an IPv6 address and we want to communicate on the network, for example, this Windows 8 machine wants to send a packet out to the rest of the internet, how does this device learn what the MAC address is of the router? Now, in IP version 4, we use something called ARP, Address Resolution Protocol, and it worked like a champ, and it still does work like a champ. In IPv6, we don't have ARP, and we don't have broadcast. Instead, we use neighbor discovery. And specifically, they call it the Neighbor Discovery Protocol. What happens is this Windows 8 box says, okay, I know the IP address of my default gateway. I just don't know his MAC address. I need to find it. And the Windows 8 box will send out a neighbor solicitation to the solicited node multicast group address that he believes anyone who owned this IP address would have joined, and the router gets that and he responds back with a neighbor advertisement. So solicitations are asking and advertisements are giving the information that was asked for. So how exactly does Parasite 6 fit into this? Well, Parasite 6 is going to be running on our Backtracker Kali box, and after we enable it, it's simply going to sit there and listen for any solicitations. And guess what? It's going to answer. But instead of answering with the correct layer 2 information, it's going to answer with its own MAC address. And when you turn this on, it does it for every single solicitation that it sees. So you can basically spoof the entire network that you're on, the entire layer 2 domain that you're on, because the Backtrack/Kali machine, when it sees a solicitation, it'll answer back saying, oh yeah, here's that layer 2 address. And then it can refresh that like every 5 seconds for every address that it's spoofing. So effectively, we have a man-in-the-middle attack. Now, it's not quite a man-in-the-middle attack yet. If we've just launched this attack, it's a DOS attack, because the frames at layer 2 will be forwarded to our Backtrack/Kali machine, but we're not going to forward it by default. We also need to enable IPv6 forwarding. We've done this several times with IPv4 based on man-in-the-middle attacks. We also need to do it here with IPv6, but the location for that forwarding file that has that little on bit set to yes. So we'll set the forwarding bit to a 1, and then we'll launch Parasite 6, and we're effectively a man-in-the-middle attack. And this is the topology that we're going to use for our demonstration. So our first victim is this Windows 8 machine, and I just want to do a couple basic commands to do some verifications. Do an IP config. So we'll do an IP config just to verify what our addresses are. I'm going to scroll up just a little bit here. So here's our link local address. We have a couple of global addresses. One we can use for privacy purposes, so we can randomize it periodically so people can't track who we are and so forth. Then we also have the IPv4 related information, which we aren't too concerned about. And we have a default gateway of FE80::1. That's the link local address of router 1. Again, router 1 has a global address of 2001::1. It also has a link local address of FE80::1, which is right here. And it also has a MAC address of 4 zeros and then 8 ones. So it's very easy to identify. So let's test and just verify that we can ping our default gateway. We'll do a ping of 2001::1, press enter, and sure enough, and if we look at the equivalent of the IP version 4 ARP cache, which in IPv6 is the IPv6 neighbor cache, we can do that as well. Let's use NetSH or NetShow for that. We'll do NetSH, And I'm going to specify from here that I want to take a look at interface IPv6. And then from here, we're going to do a show neighbors. And that will show our layer 3 to layer 2 mapping. So the part I want to focus on is this. 2001, which is our global address of our default gateway, maps to the MAC address of our default gateway. Perfect. And FE80::1, we also learned this. And those were learned via NDP, the Neighbor Discovery Protocol. Initially, there were router advertisements that had this information, but if we ever needed to ask for that again, we'd do another solicitation. So all we need to do is take our backtrack system, tell it to go ahead and run this amazing program called Parasite 6. It will listen for any new solicitations, and it will spoof with the layer 2 information of its own MAC address. So we can poison this guy. We're also going to poison the router and anybody else who happens to be unfortunate enough to be in this VLAN. And let's bring in the Kali box. I am using a virtual machine for this demonstration. It was the closest one that was reachable. And I've opened up a command line shell. And let's go ahead and run the actual tool. Now, if we needed help with the syntax for Parasite 6, how would we get that? Well, Keith, we could do a couple things. We could do Parasite 6 and press enter, and that's very likely to give us the help. Very true. Or we could do Parasite 6 and then very likely a -H or something else would give us the same exact help information. So the syntax is Parasite 6 and then the interface that we want to use. And if we want to specify the fake MAC address to go ahead and use instead of using our own on our backtrack/Kali box, we can do that as well. The -L option is going to loop. It's going to cause it to be resent every 5 seconds to keep that poisoned information nice and current. And the -R, it's going to go ahead and it's also going to try to poison the destination of the solicitation. Effectively, we're going to do both sides and we're going to refresh it every 5 seconds to keep it nice and spoofed. Now, before we launch this attack, we're going to run this command right here, echo space 1 greater than, and we're going to write that 1 to this file called forwarding, which is in the setup subfolders. The reason that's important is because if we don't have forwarding enabled for IPv6, when we do get those packets with the frames that are addressed to us, we won't bother forwarding them on to the correct destination. So let's make sure that's set, because if we don't, it's simply going to be a denial of service attack against everybody on that network as opposed to a man-in-the-middle attack. So that is set, and now let's go ahead and run the actual attack. The syntax is pretty straightforward. Parasite 6 -LR with these options right here that we just discussed. And on this system, I'm using Ethernet 0. A real quick check with ifconfig, you could verify exactly which interfaces you have that are active, and then you could pick the appropriate one. If you only have one Ethernet interface, it's very likely going to be Ethernet 0, but it isn't always the case, especially in a virtual environment where you may have modified some of those parameters. And we'll just let it go. Now it's going to sit there listening for any neighbor solicitation messages that it sees, and when it sees them, it's going to go ahead and respond with its own address. What I also did to make this easier to see, I also modified in this virtual machine this Kali box, but it did not get a global address. So it's not going to be talking on the network very effectively as an IPv6 device with only a link local address. Let's go take a look at 26BD and see if that's in this list as well. So right here, check this out. It actually sent back a message. Perhaps it didn't send it back fast enough. Because if we spoofed a packet saying, oh yeah, that's in use, that should have caused the Windows 8 box not to use it. So we could experiment with that, say, oh, maybe that's a timing issue. It didn't get the response back fast enough based on this box, etc. But that's the process. That computer, that Windows 8 box, is not going to be happy without a global address that it can go ahead and use. Now, to demonstrate this, we could stop the attack, do a Control-C once again. Now the attack's not running. I'm just going to do an up arrow key real quick, ipconfig, just to verify that he didn't magically somehow get a global address, which he did not. And let's go ahead and bounce the interface one more time. So we'll right-click, disable, and then go back and enable it. And let's go take a look again. So I'll do an ipconfig one more time, and sure enough, now he's got no problem. He's got his global address, his privacy extension global address, and he has his link local address. He is good to go. All right, so here's another mean one that we can do to the network. Now, when we spoofed a single router advertisement from this Kali box, the devices, they grabbed a global address from both networks they were connected to. So 2001, they had an address, and then 2001, DB8, I think it was 67. Oh, it was bad, was the address that we gave it. So grab one from both. So what would happen if we pumped, I don't know, a few 100,000 router advertisements spoofing all of the source link local addresses into the network, what would happen? Well, each device on the network based on Windows 8 or other Linux boxes or Macintosh or Windows XP, they would handle it the best they could, but they're going to try to remember all that detail about all these additional routers that it thinks it sees because of the all unique router advertisements that are coming in. It's going to cause a bunch of pain on virtually every device in the network. So let's go ahead and do that right now. We'll go back to the Kali box, and on the Kali box, we're going to type in flood_router6 space and the interface that we want to do it on. And it says that every dot that's printed represents 100 packets being pumped into the network, all with these router advertisements. So let's do this. Let's go ahead and bring up, I have all this set up inside of a virtual environment right here. If you are a subscriber, which I think you are, so with your subscription to CBT Nuggets, you've also got a subscription to my GNS3 series. If you want to lab this up in a private environment, not damaging anyone, GNS3 is a great way to do it. And my GNS3 series walks you through the entire gamut of how to get it up and running and working in very, very creative ways. So in the cloud, I've got Backtrack, and I've also got the Windows 8 machine, and I've also got an XP box hanging out there. And this is gig 1/0, and the IPv6 address of R1's interface is 2001:1/64. I also hard-coded the link local address as FE80::1. So what I'd like to do is let's go ahead and let's eavesdrop right here on this interface. And we can do that by right-clicking and click on Start Capture. And then I'm going to say, yeah, I want to see that. So we'll do a capture, and then we'll take a look at the output. So what's happening is, and I'm going to pause the screen just for a moment so we can look at this. It's just pumping out router advertisements like crazy. And take a look at the source addresses. They are all over the board. So just since we started that capture a few seconds ago, that was 1,300 packets. And if I unpause the screen here, we're at 6,000 and close to 7,000. So it's pumping them out as fast as it possibly can. And that's really messing up the clients on this network. So I'm going to stop this capture just for a moment. I'm going to stop it here. I'm also going to go into GNS3 and stop it here because I don't want that running indefinitely in the background. I'm going to minimize that, and let's go back to our client. Now, just a few moments ago we did ipconfig. I'm going to hit the up arrow key. Check this out. When we hit ipconfig, and as it scrolls through, look at all the IP addresses this poor computer is trying to get for itself. So global addresses, the temporary addresses, and now we're at the default gateway portion. So if we scroll up, I almost feel bad for it. So these are all the default gateways based on the router advertisement. So there's some limit, otherwise, because we're sending thousands and thousands into the network. So these are all the default gateways that it's putting in for IPv6 based on all the spoofed RAs. Here's a whole bunch of temporary addresses based on the first 64 bits. 1, 2, 3, 4. That's this section over here. And if we go higher, we'll have the addresses right here. And again, it's trying to do one for every single network that it's connected to. And again, there must be some limit based on this operating system that would, tell it, okay, it's time to stop, or first in, first out, or something else. Let's go take a look at another victim. Let's go take a look at an XP box, for example, and see what he says. So on this Windows XP box, let's go ahead and, oh my gosh, check it out. I can't even move. Now, I cannot move the windows here. Probably the CPU on this or something is too messed up for it to even. Let me stop the attack real quick. So Control C to stop the attack, give everybody a breath of fresh air. We'll go back to the Windows XP box, and now in Windows XP, no, I still can't move it. He may be toast. He may not just have had the energy to handle all that, and he went belly up. So depending on the operating system and how they handle it, maybe with XP and the implementation of IP6, maybe it simply didn't have a limit and it tried to put all of them in there, and as a result, it is no longer functioning. Now this is a virtual machine, so no permanent damage done. I can just shut it down, bring it back up, or I can bring it back to a snapshot I had, and I'll be ready to go again. Another thing that we can look at based on that attack that just happened is how did the router handle it? And let's see how the router. Oh my gosh, my router didn't handle that either. So that was a Cisco router in that GNS3 environment right here that I was connected to, and he's down. He is no longer functioning. I mean, GNS3 says, oh yeah, he's fine, he's good, but he is no longer running. So based on that attack that I sent with those router advertisements, for whatever reason he couldn't handle it, he is no longer functioning. To start him again, I could right click, I could say stop, and then restart him, and I could get him back up and going, which is effectively having to reboot that router to bring it back up. So I have rebooted R1 inside of GNS3, and there we go. So he's back up and happy. And it actually could have been several of the previous attacks that router just couldn't deal with that caused him to have grief. But certainly he was dead to the world, not even responding at the console port. So for things like that, if you want to test it, which I strongly recommend, you could launch an attack like this. Let's get a baseline first. Go back to your router. Again, in a test environment, let's do a show, process, CPU sorted. And you'll notice up here at the top, so because he just booted up, he's at like 10% utilization. So on R1, if we wanted to find out what really caused him grief, we can do a show, process, CPU, and so we have a process of about 8% right now, which might be average for a various network. And he's got some NAT and some other things going on that he's doing at the moment. So let's say the baseline is 8%. In fact, let's do one more little test. I'm going to hit Q, and I'm going to do that command one more time. So 8%, 9%, no problem. So let's go ahead and launch that same attack and see if that's the one that really gave him grief. So we'll do a flood router 6 Ethernet 0. And again, every dot represents 100 packets. Let's go back to the router. So he's complaining about some hop count setting in neighbor discovery. That's no problem. Let's go ahead and do a show process CPU. Yeah, look at it climbing right here. So right now it says 56, and it's just going to go up from there. So let's go ahead and do it one more time. Now it's 72. Yeah. So it probably just got to a point where it got to close to 100%, and he had nowhere else to turn, the poor little router, and it simply went belly up. Or at least it wasn't responding to any commands at the console port, which is currently where I'm connected. So this little asterisk right here represents where I'm currently connected, and logically, in this GNS3 environment, I'm connected directly to the console. So it doesn't even need IP connectivity to talk to me. It just has to be willing to respond on a console port, which it wasn't. So if we do that one more time, show process CPU. Yeah, so it's 91%. And so it's very likely this attack that left running for quite a while is what caused this router to go belly up. Now, in saying that, I realize I should probably avoid doing that again. So I'm going to do a Control-C now, stop it, and hopefully the router will continue to respond to me, which it is at the moment. That's fantastic. Another attack that we could launch is very similar to the flooding of router advertisements. It's flooding neighbor advertisements. Because IPv6 keeps track of the layer 3, layer 2 mappings of neighbors it knows about, if we did the same kind of a technique, but instead of router advertisements, we flooded neighbor advertisements, it could also disrupt the network. So the syntax for that is very similar to the previous. It's flood. In this case, it's advertise 6, and the interface we want to send it on, and it's pumping these out like crazy as well, too. So this is bothering all the devices on this subnet of 2001://64 because everybody has to process these. I'm going to go ahead and stop that with a Control-C. Another really great tool that will help us to identify how IPv6 was implemented specifically on a host is to run a tool called Implementation 6. Now, this is also from the THC group, and the syntax is Implementation 6, the name of the interface you want to use, and then the target you want to send this to. So what's happening right now, 2001:1 is the IPv6 global address of our default gateway, and we're simply sending a whole bunch of different packets. We know it's handling fragmentation. We know that it supports source routing, and because basically the response that we got back. So this is going to go through like 50 plus different types of scenarios asking the router, not formally saying, hey, do you support this? But by sending it packets, and based on how those packets were replied to, it makes deductions that, okay, they're supporting this feature, they're not supporting that feature. And this can benefit us how? It's when we're trying to determine what features or functions we might be trying to leverage, take advantage of, or compromise on a device. Of course, all within a test environment where you have authorization to do so. And at test 54, it's doing a ping. And we might say, well, why is it doing a ping again? It did a ping way at the beginning. Why is it doing a ping at the end? It's possible that some intrusion prevention or detection system saw our traffic, considered it to be a little bit too much, and stopped allowing that packet or those packets through. So doing a ping at the end just helps us verify some of the results in that we didn't have an intermediate or that device itself filtering all future packets based on some point in our questioning. For the Smurf attack, all we're going to do is we're going to spoof who the attack is coming from. For example, if we say Smurf6, that's the name of the command, and then put in the interface we want to use, in our case it's going to be Ethernet 0, and then we say we want to spoof 2001:1, these packets are actually being sent to the multicast all nodes group, FF02::1, which means everybody gets a copy of this ping request. However, the source address is 2001::1, which is the routers. So individuals who reply to this traffic, they're going to be replying back to the router who's going to say, I never asked for this. And it's simply a great way to eat up a lot of bandwidth and tie up a lot of resources. So what might be fun here as well is let's open up GNS3 again, and let's just put a packet tracer right here. Now you could also simply open up Wireshark in another window right on Backtrack or Kali and look at it from there, but that's also going to, if you're remotely connected to that Kali box, that'll also show you the SSH and all the other traffic that's going along as well. Doing it this way in a test environment gives you a nice clean option of looking at just the traffic on a given segment of your network. So I'm going to right click, say start capturing, click OK. So I'm going to go ahead and stop that. And I'm also going to go back to GNS3 and say please stop the capturing right there so it's not capturing the background anymore. And if you look at the content here, so it says it was sourced, this ping, from 2001::1. That's not really true. If you look at the layer 2 address, the layer 2 address of the source is 0000 dead beef. That was the writer of this tool being very creative with what source MAC address he wanted to use, but that's actually coming from the Kali box that's sending this attack. The destination address is the FF02::1, which is the multicast all nodes group, and let's see if anybody's responding to this. So if we have any takers, they would be responding to this. Look at this. I've got nobody responding back to it. Now that's healthy because in a good network environment, if we get an ICMP message that's sent to the all nodes multicast group, we should not reply to it. However, some devices aren't quite that smart. And to demonstrate that, let me go ahead and close this capture for a moment. And let's go back to a Windows XP box, which I think is, he was totally owned. That's why he didn't respond. I'm going to simply refresh this box. I'm going to say, go ahead and power off the machine. It's toast. And I'm relaunching that box inside of VirtualBox. That's my virtual environment I use quite a bit for building networks and putting devices all next to each other. So because he couldn't respond, that's why he wasn't. However, the protocol stack implementation on different platforms isn't the same. So Windows 8 versus Linux versus Windows XP, you might have some devices that do reply, which they shouldn't, to a ping request that was destined to the all nodes multicast group, and you have other devices like Windows 8 that shouldn't. But I want to go ahead and verify that's the case. So this Windows XP box is booting up. I'm going to go ahead and let him do that. Let me minimize him for a moment, and let's launch this attack again. Oh, actually the attack was running. So let's give that Windows XP box just a moment to come up. Then we'll launch the attack again and see whether or not he is going to respond. So I'm going to go back up to my GNS3, right click here, say start capturing. Stop the capture here as well. And here's what I was looking for. This is the actual IP address of our Windows XP box. So if we bring up Windows XP and we go to command prompt and do ipconfig and we look at the last digits here. So the last digits are B40B, and if we look at our trace, that is exactly the last 4 digits that is replying. So what happened was the XP box got this request right here. So it got this request, ICMP ping from 2001::1, which is spoofed from our Kali box, going to the all nodes multicast group, and the XP box said, okay, I need to reply, and it replied back. So it replied from itself to the global address of the router, who then got that packet and said, I didn't ask for this. It wasn't useful, but we're chewing up bandwidth and we're chewing up resources on that router because it has to deal with every single packet that comes in, says, do I need this? Is it for me? Is it applicable? No. Discard it, on to the next packet. So if we leave this attack running just for fun, which it is at the moment, let's go ahead and let's just do a show process CPU. And look at that. We are totally chewing up the CPU resources on this router. And that's primarily because it has to go ahead and address every single one of those ICMP messages that's going to its IP address. And most of this is courtesy of our good friend Mr. Windows XP, who is replying over and over and over again to all those ICMP requests. See, 1 or 2 bad clients, or maybe not well implemented clients, can have a negative effect on the entire subnet. In this video, we've taken a look at some of my favorite tools in the world of IPv6 from THC. I would strongly encourage you to practice with them in a test environment where you're not going to destroy anything. See, in this demonstration, I had not intended to blow out the router. I had not intended to lock up the XP box, but both of those things happened by simply running these commands. If that happened on a production network at your hands, that would be very, very bad news. So I've supplied for you in the Nugget Lab download area the actual commands that I've used in this video. So if you want to replicate those again in a test environment, you can do so. I'd also strongly encourage you, if you're brand new to IPv6, go and check out the IPv6 Nugget series on IPv6. It's fantastic. I think you'll love it. I also have the GNS3 inside of CBT Nuggets as well. So take advantage of all those resources with your subscription. I've had a great time. I appreciate the time you've spent with me. I hope this has been informative for you, and I'd like to thank you for viewing.